Well, continuing with triple integrals. And we are going to study these integrals in spherical coordinates. So let me introduce spherical coordinates first. So we have this X, Y, Z space. And let's suppose that we have a point. Which we call P. Okay. Now from the point P, I draw a perpendicular to the XY plane. And we look at the point in the XY plane, which is the projection of P onto the XY plane. And the coordinates are, of course, X and Y. And then from the origin, I can join the origin with this projection here. The radius here is R. Okay? But we are not so much interested in R, in spherical coordinates. But the angle theta is still important. This is theta. Okay. But let me warn you that in some books, they use a different letter for this angle. They use the angle phi. But let's try to follow the old tradition of using r and theta for the polar coordinates in the xy plane. Okay? Now, what are we going to look at in spherical coordinates? Now, there is one more feature about this XYZ space. We can look at this point. And join it to the origin. Okay? And people usually denote the length of this radius by rho, which is the Greek letter P. Okay? Now, if you look at this radius here, not this one, not all, but this one, rho, you can rotate it about the same axis, and you are going to get a cone. All right? Now, there is an angle called the azimuthal angle, which is this angle. Okay? Now, this azimuthal angle is denoted by phi. Like the empty set. Okay? But this phi is used to mean many things in mathematics. And in this case, is the azimuthal angle. Okay. Now, we are particularly interested in rho, in phi, and in theta. So I can say that P can be denoted by rho, by phi, and also by theta. Okay. And these three variables here, these three coordinates here, specify the point P. And we call this the spherical coordinates. of the point P. Okay. Now let's try to see the relationship between x, y, z and rho, phi, and theta. So we have the following formula. Let's look at x first. Well, we know that this is a right angle. This is also a right angle. So is this one. So what is x? X, as usual, is equal to r cosine theta. But as I said, we are not so interested in R. So let's change it to rho. As I said, this is a right angle. So this R here is equal to what? If this angle is equal to phi, this angle is also equal to phi. Okay. So R is equal to this rho psi phi. So x is actually given by rho psi phi cosine theta. Now let's look at y. Well, y is here. And remembering that this is a right angle. Then, what do we know about y? Well, this is R. And then, what do you want to find? You want to find this point. But this is basically polar coordinates. So it's going to be the same as this length. This is also y. If this is y, this is also y. And this is also a right angle. So y is equal to r psi of theta, which is well known. Now, again, we want to replace R by something else. As before, is rho sine phi. And then we have sine theta. Right? And finally, we want to find z. This is z. So what's z equal to? Z is very simple. It's just rho cosine phi. Okay. Now let's also specify the range of each coordinate. Now, as before, this angle theta is usually taken to be from 0 to 2 pi. Now, the interesting angle is this azimuthal angle. Now, this ray here can come from this z-axis in the upward direction. And it can go down to the z-axis in the opposite direction. So, what is the angle? Or what's the range of the angle? Well, if it's in the positive direction in the z-axis, phi is equal to 0. Now, if it aligns with the z-axis in the opposite direction, the angle would be pi. And rho being the radius. As I said before, the radius is always taken to be positive. So rho is taken to be positive or equal to 0. And when rho is equal to 0, then we are at the origin. All right?
Professor, just a quick question.
Yeah.
So the signal, the empty set from 0 to pi, why is it from 0 to pi?
That's not the empty set.
Oh, what?
The angle.
Oh, the angle. Sorry. So why does it go from 0 to pi?
Well, I said that before. This radius here can be along the z-axis in the positive direction, in which case is equal to 0. Right?
Yes.
But it can also align with the z-axis in the opposite direction, downwards. And then the whole radius here will come down. And then what is the angle? The angle would be
Pi.
Yeah.
Oh, got it. Thank you, sir.
okay. No, this is not the empty set, it's an angle. Okay, all right. So you can see that this spherical coordinates are actually more challenging than the cylindrical coordinates. The cylindrical coordinates are basically polar coordinates. And the spherical coordinates are the genuine polar coordinates in 3 dimensions. Okay? All right. Now let's take a region in R3. And suppose that we have a continuous function defined on this origin. So we let f be a continuous function. On the region. Now the question is the same as before. What is this integral? Triple integral. On E of the function f at x, y, and z with respect to v. And this time, we want an expression in spherical coordinates. how are we going to answer this question? The crux of the matter is what is AV in spherical coordinates? So again, the real matter is the following. What is AV? In spherical coordinates. Okay. Now, if you come as a surprise to you that this is not at all simple. So let me do it here because at least I can hold the board from shaking. So we have the X, Y, Z space, which I have mentioned again and again as a backdrop to do a lot of things. So this is X, this is Y, and this is Z. Okay. Now, I have a region which I am not going to draw it. Otherwise, again, everything would be very messy. So imagine that there is a solid here. And then I am going to take a point inside the solid. Okay. All right. Then I am going to drop a perpendicular to the XY plane. Okay. This point here has polar coordinates, rho, phi, and theta. And I am going to look at the radius joining the projection and the origin. And then we have an angle theta here. Okay. I'm not going to write down theta. Now, let me write down something. So I let rho phi and theta be a point in E. I have the angle theta here. Okay. Now, I am going to let d theta be an increment in theta. Then this increment would induce increments in the other two variables, phi and also rho. Okay. Now, let's say that this is the increment. Okay. Well, actually, the increment should be inside. But let's take a negative increment. It doesn't matter. Okay. So we have something like this. Okay. This is d theta. Okay. And what are we going to look at? Now, the radius here is r. So what is the length of this arc here? The radius is r. So this is going to be r d theta. This is r d theta. Now, let's try to look at things above. Maybe I will take away this point first. Okay. So I look at two rays coming out of the origin. Okay. So there is an angle here. Okay. Corresponding to the increment d theta. And this is d phi. Okay, so let me denote it like this. This is d phi. And this is the point rho, phi, and theta. The whole point is to blow up that point a little bit towards spherical rectangle, a very small spherical rectangle. So like this. And again, we zoom in and make it a bit bigger. Okay. And we look at two similar rays. Here. Then what are we going to get? This is the point rho phi theta. Okay. And I am going to look at the following thing. Okay. And then this one. We'll go to here. And rejoin this. So this is more or less like a rectangle, a curvilinear rectangle. But in fact, it can be considered to be a regular rectangle because everything is very small. I should not put the point here. It stands in the way. Let me not mention it. Now, this point will come down. And this point will come down here. And then we join these 2 points to have another curvilinear rectangle, which is a bona fide rectangular rectangle, the XYZ rectangle, because everything is very small. And I assume that you can see all the lines because we have been assuming that everything is transparent. Okay? This is what people like, transparency. Or at least that's the slogan. All right. Now, so this point is blown up to a rectangle. Doesn't look like a rectangular rectangle. But in fact, it's very small, so it can be considered to be a regular rectangle. Now, let's look at some dimensions. Well, the length of this is rho. So I have d rho. Okay? Which is the same as this one. This is d rho. So from this d theta, we have induced increments in rho. And d phi, what about phi here? See, this is how this radius is rotated down. That's d phi. Which means that this is also d phi, or this is d phi. Okay? Now, what is the length of this one? If this is d phi, this is also d phi. So what's the length of this arc? Anybody?
Rho d phi.
That's good. Yeah, it's rho d phi. Now, keep in mind that we don't like R, right? We don't want R in our spherical coordinates. So this means what? This length here, what's this length?
Is it rho sine phi d theta?
But I see how it goes up there. But let me write down rho sine phi d theta. And how did it go up? So it must be this length here. This is the only thing missing. or this one here. So this one is actually the elevation of this up there. Okay. So the length of this, or the length of this one, is rho psi phi d theta. So this singular point here, okay, which is in the solid, can be blown up to a rectangle. Then dV of the rectangle or we can call it the spherical rectangle. Is given by the following. Wait, so wait. I don't want to bend down the weight. So it's given by the following thing. So is this length times this length times the height. Is the area of the base times the height. Well, the area of the base is rho d phi times rho psi phi d theta. And then you have to multiply it by the height, which is 0. So it's rho squared psi phi d rho d phi d theta. Right? That's dV. Now, once you have dV, the rest is easy. Keep in mind that we have a point in the region. We blow it up to a very small rectangle, spherical rectangle, which can still be considered as a point. Okay, something like a cell. You need to have a very powerful microscope to see this cell. And then if you want to find everything in the solid. Then all you have to do is to let the point flow around the solid. In other words, you let that spherical rectangle to flow around the solid. Each such spherical rectangle has a volume. And then you add all them up and you get the volume of the solid. Okay? The same idea that we have been using. Except that the technicalities are more colorful. So, I mean colorful in structure. So, our triple integral is equal to the following thing. Now, you have to fix the endpoints. But for now, I am not going to do it because you have to look at specific examples to fix the endpoints. So it's the triple integral of f. What is x again? Do you still remember? Is rho psi c. Cosine theta. And then y is also rho sine phi. But sine theta. And z is rho cosine theta. And then we have dv, and dv is this one. It's rho squared psi of phi d rho d phi d theta. And as I said, the endpoints here have to be determined by the geometry of the region E. Okay. Yeah, perhaps I will stop here today. Oh, still over time. What's happened? I don't know. I don't know what. I hope I have some time left. Yes.
Will we have this on our test?
Well, you can answer this question. What's your answer? Well, on Monday, well, on last Friday, I already gave you the syllabus. So what's the answer? Yes or no?
No,
No.
it's up to 15.7, I think. This one's 15.8.
Yeah. I said up to cylindrical coordinates. Okay. Well, unless I don't keep my promise. But I usually do. I actually always do. Okay. So this is 15.8. This is spherical coordinates. Any other questions? Well, there was a remark saying that the diagram is very confusing. Okay. When you try to draw three-dimensional objects on a two-dimensional plane, you need some imagination to see things. Okay. Because you are drawing some higher dimensional objects on a plane. And then you have to use perspective and so on. Projections, perspective, and so on in order to visualize it. Okay. But nowadays, there are some computers which can actually plot these graphs much more clearly. Okay. So if you can afford it, you can buy some of these softwares. Well, even the book, the figures in the book for three-dimensional objects printed on paper is confusing. Okay. And this is why I spoke very slowly to explain each part. So, any questions? I will do an example on Wednesday. Okay, hearing no questions. So let's finish for today.